In this video, we are going to understand the switching characteristics of a power BJT. To explain the switching characteristics, we have taken the BJT with the terminal base, ammeter and collector. Base and ammeter are connected to the input and collector and ammeter is connected to the output. Now in the output, if we take a supply voltage VCC, let us take 100 volt, and with a load resistance RL, there should be a current flowing in the output side. But since the switch is off, this current will be zero. So IC will not be there. So if I write the IC, what will be the equation? The IC will be nothing but VCC minus the drop over here is VC and divided by RL. Now, why this IC is 0? That means the VCE is nothing but these two are equal value, and when these two are equal, IC is 0. Now in the input end, there is a current IB, and the current IB will obviously, by using KVL, it will be VS minus VB, the voltage across the base ammeter voltage, divided by RB. Now in the input end, the current will be there only if there is a VS. Now if this current is positive, then only this is going to turn on. And once it turn on, this IB need to be there. As long as you want to turn on the switch, the IB has to be there continuously. That's the limitation of the power BJT compared to MOSFET and IGBT. Here, you need to give the IB continuously. That means in the base end, there is a supply has to be positive continuously. Then IB will be there. If IB will be there, then this is on. If this is on, in the secondary, in the output side, the current will flow. And the current will flow only if this VC, the drop across the collector and ammeter, will decrease, then only this IC will exist. So here we have the time which is divided into 9 different zones to understand the off and on state. In the first we have the off. So here in the fifth we will try to keep it completely on. Then we will turn off. And at the 9th we will make it completely off. To see that, we need to have like supply voltage. Supply voltage Vs, we will give a supply in this manner where initially the Vs can be given as minus Vs, then after when we want to turn it on, we give it a supply as Vs. So this Vs here is represented as Vs. In the y-axis, in these two, we are representing the VB for input for base ammeter voltage and the base current. And also we are observing what is the output collector current and collector to ammeter voltage. So Vs is a supply voltage that we want to turn it on after the stage 1 and keep it on for stage 2, 3, 4 and 5, then we want to turn it off. So when we give a base voltage from minus Vs to Vs, so we would like to see that what will be the IB and VB. So let me write here as minus Vs. So if I write minus Vs, this VB, there is initially it would be 0. So whatever the current is minus Vs by RB, so the IB current will be there. IB current, this will be the value of IB current. Now VB is initial stage, it would be maybe 0, or if the supply voltage is minus Vs in initial stage, this will be also minus Vs. So this change in the value of this will not be reflected. So you have the VB which is minus Vs then this will going to be changed in the stage 2. So this is what happened in the input side. In the stage 1, everything is off, and the stage 2, the moment we are giving the supply voltage Vs, we find that IB will come into picture, and this VB gradually from minus Vs, it leads to 0. So we will represent it like this. So once it is 0, this value of minus Vs and minus Vs, 2 minus Vs by Rb, now it has become minus Vs by Rb. So this will decrease down. Now what is the effect on the output side in stage 2 and stage 1? In stage 1, when it is off, obviously when it is off, VCE is equal to VCC. That means these two voltage, ये दोनों voltage समान है, right? they दोनों समान होंगे, तो x minus x is 0. So IC is 0. So IC is 0, and VCE is having a supply voltage value, that is VCC. So these two values are same. In the stage 2, we are expecting that there is a current in the IB, in the base there is a current, so there should be a drop in VCE, but it is not possible because this power BJT has got an extra layer N minus, which is lightly doped. So magnetic charge carrier is being injected in this lightly doped layer. So as long as it is not filled completely, so this VCC will exist across the VCE. That means the collector emitter voltage will have the same voltage of the supply voltage, that is VCC. And obviously if that is there, the current will obviously be 0 in stage 2. So we find that even though we turn it on, there is a change in the input side, but there is no change in the output side, and this is because of N minus layer, and that is why this is called the delay time. Now after the delay time is over, now this is get filled, N minus layer get filled, so we don't need, then this will behave normally. Now the VCC will try to fall and IC will try to rise, and this time will be called as the rise time. Other things will remain like this, and this VB will now goes to the forward voltage drop of like 0.7, and this drop will exist. So obviously this there will be a little bit of drop in the current, otherwise it's nearly same. And in stage 3, there is a rise of the current, collector current, and fall of the collector emitter voltage. And in stage 4, this will settle down, like there is a complete settle down of the IC will attain a total current of what is supposed to be that VCC by RL, and VCE will come down to 0. So you have got a settling time. And that is why 2, 3, 4, this much time, delay time, rise time, settle time, this much time is required to turn on a power BJT. So all the characteristics remain like this. So in stage 5 we can say that this is completely on VCC, this is voltage across the collector and emitter, this is 0. So we have got only current like this. So in stage 5 we say it's completely on. Now we want to turn it off. So when you want to turn it off, you drop the voltage across the supply from Vs to minus Vs. So obviously when you drop the voltage, the current will reverse. So now from like this is 0.7, let us say. Now if you change the polarity of this from Vs, it is going on, now you convert into minus Vs, so obviously the current will reverse. The current will be reversed over here. This current will reverse, but this will be in opposite direction. But this voltage across the VBE base emitter will not going to change immediately. Because the N minus layer, all the magnetic carriers are injected into it. So when it is a negative current, these carriers what is injected need to be taken out. Unless another is not taken out, the base emitter voltage drop is still positive. So the IB current is negative and other things remain same in the stage 6. Now VCC still 0, current still 0, still full. The collector's current and the output current, this output current IC, they are not going to react in stage 6. And this time is called the storage time. Storage time means whatever the magnetic carrier charge, this is injected, that is need to be taken out. So once it is taken out, in stage 7, the current will fall. That means the output will going to be activated in stage 7 after the storage time. And the collector emitter voltage will give rise again to VCC. So there is a rise of the voltage drop across collector emitter and fall of the collector current in stage 7. But until then, this base current is still negative. This base is not getting any reaction over here. The current is only reversed, but the base emitter voltage is not reacted. But now in stage 8, once the supply current is blocked, now this current is no longer coming in, and the voltage is across the collector emitter has developed to VCC, then this current, base current which is there, will come down to 0, because the base emitter voltage will now develop this voltage to minus Vs. So minus Vs, minus of minus Vs will be 0. That is, from this it will come down to minus Vs. So if this is VB is minus Vs, so IB is equal to 0. So IB will come to the 0 value. And the collector emitter voltage is still blocking with the VCC, and the current is now stopped. In stage 9, it is completely in the off state. So by summarizing this, you can see that in the on and off stage, during this time 3, this is the time 3, we find that this is the rise time, and in stage 7 we find there is a fall time, and before 3 there is a storage time, and before the fall time, before 3 there is a delay time, and before the fall time there is a storage time. That's why what we observe here is, to take it completely off, it takes time 6, 7, 8, and to make it completely on, it takes a time of 2, 3, 4. So the power BJT, the advantage is that it has a very low conduction loss, but it has a disadvantage is that it takes time to turn on. When we say it is taking time to turn on, that it's taking time in terms of milliseconds, compared to the other switches where the turn on time is in microseconds. So, but the problem is that the turn on time is fast, but the drop is more. But in power BJT, the turn on and turn off time is more, but if it is on for longer time, the drop is very low, so it is good. So when the switching time is required, that is fast turn on and turn off is required, then we go for a MOSFET or IGBTs. But if we need a longer duration of turn on, then power BJT is good. But another drawback is that the base current need to be there as long as the collector current is flowing. Moment we remove the base current, the collector current is removed, which is not in the case of the other switches. There, once you give the base voltage, once it is turned on, no further required. But in power BJT, The condition is that IB need to be there continuously, and turn on time and turn off time is here more compared to other switches. So IB need to be there. This is the problem, and the good thing is that on-state resistance is low, so the loss is low during the on time. Thank you very much.